Good morning. I'm going to talk about twinning. I'm going to start with giving some definitions. What is twinning? There will be a question in the very beginning. We are then going to look at different types of twinning. We're also going to look at what is not twinning. And we're also going to talk about how to deal in macromolecular crystallography with a twin. So the first question, The first question I would like to ask is this a twin? And we are going to answer the scientific question in a democratical fashion. So who of you thinks this is a twin? Please raise your hand. By the way, if you don't raise your hand in one of the two answers, that's not good. So who of you thinks this is a twin? Please raise your hand. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Who of you thinks this is not a twin? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So about 50-50. Now, obviously, this looks like a twin. Just because it looks like a twin, that does not mean it's not a twin. Sorry, my computer keeps playing up. There we are. This is a twin. It's a macroscopic twin, so you can see it's a twin. It's still a twin. Because a twin is two or more crystals of the same species joined together in different orientation. And this is two or more crystals of the same species joined together in different orientation. So because so many macromolecular crystallographers think this is not a twin, I have had entire lecture halls saying this is not a twin. I brought some macroscopic mineralogical twins that you can actually touch. So you can have a look at them. And if we've got some time in the end, I may ask some questions about them, so have a good look. And I just start passing those here and those there. Now, when you have a twin fraction. That's, if you've got the fraction, how much of a reflection will be made up of one domain and how much will be made up of the other. Basically, how much volume does one domain have opposed to the other. And the twin law is the operator between the two conjoined crystals, right? It's the operation that transfers the orientation of one domain into the other. It's also called twin operator or twin law, and it's an additional symmetry operation in reciprocal space. Now, how do we get a twin? There are two different ways. They both result in the same twin. So we can't tell once we see a twin how it came to be, but we can watch it grow. And this is a crystal happily growing layer after layer, and then one of the asymmetric units, so one of the proteins perhaps, is misoriented. Now, this leads to misorientation of the next one, and as the crystal continues to grow, we get a second domain. Now, this is still the same crystal species, but it's in a different orientation. The other way to get a twin is that two nuclei are growing very close to each other, and at one point they touch, and they continue to grow, and they grow into each other. The result might look the same. We don't know. Now, there are macroscopic twins, like the ones I'm giving around, and they look like this. Now, if you see something like this in your microscope, what is the decent thing to do? Yes, exactly. Cut it and not have to listen to the rest of this lecture. Now, however, there are microscopic twins. They look fine, like single crystals, but they are twinned. Another possibility would be that you only irradiate the part of the crystal which is not having any portion of the other domain. So in order to treat twins correctly, you need to identify the twinning type, non-merohedral, merohedral, or pseudo-merohedral, find the twin law and the twin fraction alpha, and then treat the data accordingly. So easy, right? So we are going to go through these three categories. The first one is merohedral twinning. In merohedral twinning, the twin law is the symmetry operator of the crystal system, but not of the crystal's point group. So it looks in real space perhaps like this. If I show you a slice of reciprocal space, a reciprocal plane, the blue domain may give us a diffraction pattern like this one. The red domain may give us a pattern like this one. As you can see, this has fourfold symmetry through the middle. So that point is repeated here and here and here. And this one is just oriented differently. Now, if we overlay them, the result is something that looks, it still has that fourfold symmetry, but it has higher symmetry now than it had before. We've now gained, depending on how you look at it, twofold rotation here or a mirror plane. In 2D, you can't tell. Also, the intensity distribution has changed because every reflection, every point here is now the sum of two intensities. And since the intensity distribution has a certain shape and the sum of two intensity distributions has another shape, we can exploit this to identify these twins. Because clearly, there are no split reflections here whatsoever. The two lattices overlap exactly. And that's a typical sign for a merohedral twin. So that's the lower correct symmetry you expect for one domain. And you can see how the twin law is introducing an additional symmetry operation. How do I recognize a merohedral twin? It's the lower symmetry point group of the trigonal, hexagonal, tetragonal, or cubic system. These are the ones where you have two different Laue groups. Symmetry looks possibly higher than it really is. Intensity distribution has changed. You can also see it from our merge. I'll show an example in one of the next slides. There are typical space groups where this happens preferred, and you can possibly not find a structure solution. That's often when people cannot find a structure solution and they start looking for pathology, they look for twins. Now, as I said, it can only happen in trigonal, hexagonal, cubic, and tetragonal. And a typical case is, for example, P41 that gets a twin law, which is a twofold axis, and then looks like P4122. Hence, going from 4 to 422 point group. Or 3-1 looking like 3-1-1-2 or P6-4. Merohedral twinning occurs more frequently than commonly recognized. I said it's an indication that your structure doesn't solve, but the reality is that many twins actually can be solved in the wrong space group and get deposited to the PDB. Depending on how conservative you are, about up to 30% of the PDB are potentially twinned, and the twinning has been ignored in the data processing. Which also means that this could be a good reason why an R value is very high, because twinning has not been recognized and just ignored. Now, we need a test for that intensity distribution thing. The first test we look at is the H test. For the H test, it's important to recognize that we are taking two intensities that are related by the potential twin law. There is only a limited number of potential twin laws that basically transforms the lower point group into the higher point group. So we can make a good guess. We take those two intensities, take the difference between them, take the absolute, and divide by their sum. We then do a cumulative probability distribution of this H value and plot it. And the plot will possibly be more easy to understand. So what we would get for a certain structure would be the dotted line. You have these three kind of like lines to see different alphas. Alpha is the twin fraction. From a high alpha to a low alpha. Now, if you get for a structure a dotted line like this in an H test, you see there's N of H, there's H. What do you think is the twin fraction? Just make a guess. 25%, yeah? Pretty good, I would say. There's the slope of, and that's often a thing, and you can ignore that slope of. So actually where most of the graph is sitting is interesting. But you can also see that the determination of alpha is not very exact. So if you have a merohedral twin and you've done the H test and you are putting this in your paper, you should not give the twin fraction to the third digit because it's a statistical, derived, not so certain thing. Possibly giving it to the first or second digit is good. Drawbacks. There is one line that is totally missing here. Which line is totally missing? Half, yes. Half would be a perfect twin. Twins where alpha is 50% are called perfect twins. And there is no line for half. Why not? Well, if you think back to H, if we have the same intensity for the first and the second as we would have in a perfect twin, that would result in H being 0 and we could not make a graph. So we need another test. And the test we need is the L test. That's the formalism for it. I put it in the slides. You can download them from my homepage if you want to see it. It's the thing that is important here is we are now taking two intensities that are only near to each other in reciprocal space. They are no longer related by a potential twin law. For the L test, we just take two intensities that are close in reciprocal space. And actually, how close they are is an important choice. And then we get a plot like this. And we are only looking here at the red and the yellow line for acentric reflections. The centric one is often omitted, but I've drawn it here so you know it exists. An acentric reflections, a perfect twin would be on the red line. An untwinned structure would be on the yellow. If we get something like this, what would we have? Yes, exactly, a perfect twin. And you are this is also known as the Yeats-Padilla test. So the L test is also known as the Yeats-Padilla test. So both of these tests can be generated with a number of programs. Pointless, C-truncate, D-twin in CCP4, but also Phoenix X-triage. There's a server for them. So there's various possibilities. It is also important to note that because of the changed intensity distribution, E squared minus 1, which, are there any small molecule crystallographers here today? 1? Possibly 5 in a past life. So if you are a small molecule crystallographer, you know E squared minus 1 because that's how you determine whether you've got a centrosymmetric space group or not. But it's also too low, like way too low for twins. And that is one of the reasons why, for example, Shellix and X-triage are giving you these values. So if you are wanting to do this in the old CCP4 GUI, you run truncate in a very normal fashion, just giving you empty set file and click run. And you get two plots which look like this. So after the last 5 minutes, if you were here, this should now look vaguely familiar. There's the H test, giving you a twin fraction of about 0.4 here, and it's sloping off again. And then if we look to the L test for the same structure, we can see it's just below perfect twin, again confirming that we have 0.4. Now, our merge, I said, also behaves strangely. So you can see that in this case, mersaicidine, a small peptide, the e square minus 1 was below 0.7 something, so it's too low already. But then we integrate the structure in different space groups. Now, for the very low symmetry, for P32, we get 5%. That's good. We believe the crystal has this kind of symmetry, but perhaps the symmetry is higher. So we process it in P32 2 and in P32 2. And now what you see is that these two values are vastly different. Now, if both of these symmetries would be totally not true, they would both have high values, perhaps in the 40s. But the crystal seems to have some kind of resemblance to this. And that's because it's twinned. And that would then be the potential twin law. So this is also a method to find potential twin laws. And it's often, so behavior like this can often be a hint. Now, how do we treat merohedral twins? We've identified them now, supposedly using the H or the L test, or perhaps R merge or E squared minus 1. We integrate them always in the lower correct symmetry, never in the higher one, because the higher one is wrong. We want the symmetry of one domain of the crystal species. For structure solution, we use molecular replacement, which usually works well, MAD or SAT. But we cannot use sulfur SAT because it is so sensitive to outliers and actually suffers quite a lot from the changed intensity distribution. And SIR and MIR also don't work. Now, if you've got twins, in particular, they're not perfect twins. You may have two different crystals. They're both twins, but their twin fraction is different. One has 0.2 and one has 0.3. Clearly, such crystals would no longer be isomorphous, and so we cannot use isomorphous phasing methods for these crystals. For refinement, this is fairly easy these days. Most macromolecular refinement programs are supporting merohedral twins. Some, like RefMake, find you the twin law automatically, but you still have had to integrate in the correct group. However, and the R values are always nice when you use twin refinement, even if your input structure is not a twin. So you can lower your R value by about 5% by using twin refinement on a structure that is not a twin. You can do that. I would hope that the referees are going to reject your paper, or at least say you need to do re-refinement because it's not a valid treatment. R3 is slightly problematic because R3 needs to include all twin-related fractions. So the easiest way to achieve that is actually, in such a case, to use thin shells for the R3 determination and not absolutely random reflection values. Also, R factors, being statistical measures that see how well your intensities fit your model, are lower because you can imagine that the distribution has narrowed by being a sum of two intensities. And this means that R values are generally a worse criterion when you have a twin. So the random R value, the R value that says nothing's been found, goes from 58.5% to 50% for twins. So this is one of the reasons why you need a much lower R value to be actually sure that the structure is going to refine. And the difference density may look different or not. If you want to use that, or again in the old CCP4 GUI, you just say intensity or amplitude-based twin refinement here. Now, to summarize, merohedral twinning. The twin law is a symmetry operator of the crystal system, but not of the crystal's point group. It only happens in tetragonal, trigonal, hexagonal, and cubic space groups. And you have an exact overlap of reciprocal lattices, but different intensity distribution, which you can exploit, for example, with the L-test. And usually you can expect good results. Let's look at the next case. Special case. Reticular merohedral is a rare case that I'm just showing so you've heard the term and can possibly recognize it if it happens to you. You get the most common case is obverse reverse twinning in a rhombohedral crystal. So you've got one domain giving you a lattice section like this, and the other like that. When you shift them on top of each other, there are a lot of reflections in this new lattice which are missing. And they form a funny pattern. So there is some kind of pattern to this, but it's not consistent with any systematic extinctions. So the typical cases are R3 looking like P31, for example. 1/3 of all reflections are missing, and they form a funny pattern which is inconsistent with any systematic absence. So this is the special case of reticular merohedral. Now we go to pseudo-merohedral twinning. In pseudo-merohedral twinning, we basically extend the concept now. Here the twin law belongs to a higher crystal system than the structure. The classical case being the structure is originally monoclinic and looks orthorhombic. So we have one domain and the other domain, and we shift them on top of each other, and then we magnify this a little bit. I hope you can see this. Now, as you can see, the overlap is now not perfect. If we would extend this quite a lot wider, we possibly would see split reflections at the edge. So split reflections at very high resolution can be a warning sign for pseudo-merohedral twinning. I could draw now in this lattice an orthorhombic centered cell. But I could also draw a monoclinic cell. The crystal is originally monoclinic. As you can see, this can only happen if monoclinic has approximately A being C and beta being approximately 90 degrees. Classical case is P21 looking like C2221. Really, really classical. There are a lot more possibilities. A big problem is sometimes to find the right space group, the right lower symmetry. How do I recognize this? I recognize this exactly like a merohedral twin. The L and H tests work for these as well as they work for merohedral twins. So no problem there. Our merge also can behave strangely and E² -1. But the overlap of the lattices might not be perfect. So if you see split reflections, you may have not a merohedral twin, but a pseudo-merohedral one. How do I treat it? You treat it very similar to merohedral twins. You can use the same refinement programs. Most programs that can process merohedral data will also process pseudo-merohedral twins. But the really crucial and difficult point is to choose the correct lower symmetry space group. So if you have no suspicion that your crystal is twinned, you will just not recognize it. And these up to 30% of the PDB that are twinned, where the L test actually said the structure could be twinned, are including, of course, also pseudo-merohedral cases. So to summarize, in pseudo-merohedral twinning, the twin law belongs to a higher crystal system than the structure. So another crystal system. You can recognize them from frames or using statistical tests, or in any other way you can identify merohedral twins, and you can usually, again, expect good results. The last case is one which is not routine in protein crystallography, but is very much routine in small molecule crystallography. It's non-merohedral twins. Here the twin law is relatively arbitrary, although it's often a 180-degree rotation. You've got two domains. As you can see, these two are the same. They're just oriented differently, arbitrary. And you put them on top of each other, and the resulting diffraction pattern is pretty messy. So you can recognize this from detector frames. Because you're not seeing nice loons, you actually see something that you really think is strange. You can also look at a reciprocal lattice viewer. Missing from this slide is the Dial's reciprocal lattice viewer, which will allow you to identify such twins. In a reciprocal lattice viewer, you would have the reciprocal lattice looking like this, pretty chaotic, but you can already see there are two different main directions. And if you index and color them differently, it becomes, and orient them correctly, you can quite clearly see these are two arbitrary oriented lattices on top of each other. You cannot find a suitable cell for all reflections. You're searching for a cell, and whatever you do, you can't find the right one. The cell refinement is difficult. You get an unusual long cell axis. So why do you get an unusual long cell axis? Any ideas? Yeah, because you can index more reflections, because also they're closer. So because you've got two overlapping lattices, you can make axes which are very short, resulting in very long axes in real space. Some reflections are sharp, other reflections are split. Here is a crystal from Madhumati Sevana's PhD thesis. Madhumati did her PhD thesis on non-merohedral twins in macromolecules, which was kind of pioneering work for this, really. This crystal is a triplet. As you can see, it has 3 separate centers. So we would have a difficult time centering this crystal, right? We could center it on the middle, accepting that we are not centering any of the domains correctly, or we can center on one of them and just try to get, so it's really difficult. We expect to get single reflections and overlapping spots. And indeed, this is the diffraction pattern we get. And as you can see, most reflections are sharp, but some are split. After indexing, things become a little bit more clear, and you can see all 3 domains. So these are the 3 cases. You get non-overlapping reflections, partial overlaps, and complete overlaps. And how do we treat it? First of all, we need to determine the cell before we can even start integration. So for indexing, we need to leave out the partial overlaps. That's the first thing we do, because the partial overlaps, we don't even know where their center is. We find a cell that then fits a reasonable fraction of spots. Then we use the not yet indexed reflections as in an alternative orientation of the same cell to index the rest and repeat as necessary. So in CCP4 currently, Feckless will do that. But it can also be done with XDS using the omitted reflections after indexing. Yes, what I said already, most from Feckless, you need to use the multi-keyword in auto-indexing. And you can do it with CellNow, which is proprietary by Bruker. Here's the second example. Now, if you see something like this in your microscope, what's the decent thing to do?
Take the one on the top.
Yeah, take the one on the top. Yeah. Just making sure you're still awake. It's cubic insulin. Now, Madhu had a PhD thesis in which she wanted to look at non-merohedral twins. So she was tasked with growing non-merohedral twins on purpose, which possibly sounds easier than it really is. So she found out that if the temperatures are very low, she gets more non-merohedral twins. This has not been a systematic study, but I would be very interested if you have any experience with temperature and twins. Now, this crystal could possibly be centered correctly with both domains because they have about the same center. If we do that in CellNow, and I'm only showing this in CellNow because CellNow gives nice statistics, you get the first domain, and it gives you this cell. We were able to index 4,000 reflections to this domain. Then we have a different orientation of the same cell, and we were able to index 3,500 reflections, leaving us with 184 that we have not indexed, which may well be noise. And we get a twin law, which is a rotation by 90 degrees about the reciprocal axis, resulting in this twin law. So that's then the transformation that gets you from one domain into the second. How do we integrate this? So we have now found the cell. We know the twin law. Now we need to find that. We could do a profile analysis and estimate the relative intensities. Very few programs can handle non-merohedral twins in this way. Saint, eval, CCD, MOSFilm, and I don't know how far Dials is with this. It can, so Dials as well. Possibly means that I need to replace some slides here. You need a special file format if you want to hold both domains, or you can merge them. There are other options. You can ignore the twinning. That can give you poor results, if any, but there are cases where it worked. You can omit just all overlaps. You get a low completeness, but you can process then, and if you use only one cell without the alternative orientation, it might get you somewhere. You can omit all partial overlaps and just do all the complete overlaps and all the non-overlaps. You can integrate the overlaps, but without deconvolution, just splitting them half-half, and that's what very many programs do. Or you can integrate both domains by profile fitting with the overlapping reflections. Good, but very complicated. So profile fitting would be something like this. We look at non-overlapping reflections. We get an idea what's their profile. Partial overlaps, we can then split up. And complete overlaps, we need to have symmetry equivalents which are not completely overlapping. Otherwise, we can't know how much of this reflection will belong to one intensity and how much to the other. It's a really difficult thing to do. Now, in reality, a partial overlap may look like this. So this is this reflection from the data set I've shown. And you can see how you could possibly split it in two different reflections. In MOSFilm, it would look like this. Scaling and absorption correction are another problem. As I said, the crystal cannot often be centered completely. So for this crystal, we could center both domains pretty well, and the scale factor, so this is number of images, and this is scale factor, pretty good, close to 1. But for this one, the scale factor goes up and down. Supposedly, the red line coming from the domain that was the farthest away from the center during the measurement. So non-merohedral twins. The twin law is relatively arbitrary, is often a twofold rotation. The recognition can come from frames or a reciprocal lattice viewer. You have no exact overlap of the reciprocal lattices. The cell determination, integration, scaling, and refinement are all difficult. Detwinning is possible, and you can use these data for structure, solution, and refinement, but you will still have problems with the R3 set. So this has just not been, there has not been enough research in this. We have problems determining R3 for non-merohedral twins, but it's shown possible to solve these macromolecular non-merohedral twin structures. If feasible, try irradiating only a part of the crystal or try to get another crystal. So this is not a twin. In this case, you have domains and they are all shifted not very far from each other, and there are very many of them. This typically happens when in the crystal preparation or during cooling, the crystal got shattered. We call this then a split crystal. As you can see, the diffraction pattern gets very messy. This is a real example of someone who was very desperate, so they only got ever one crystal, and they got only one data set from it, and that was the data set. And he came into my office and asked whether I could help him because it's a twin. Unfortunately, I could not help him because this is not a twin, it's a split crystal. And split crystals can only give you reasonable data if they have a limited number of domains. In which case, the twin law will be near to unity because the orientation will still be, after a crack, for example, pretty similar. You can also recognize these because when you do indexing, the indexing gets continuously better as the box gets bigger. And the data quality is not usually so good. To summarize, there are several types of twins: merohedral, pseudo-merohedral, and non-merohedral twins. You can never detect a twin without having the suspicion that you have a twin, And not every data set that can solve or refine is twinned. You need to actually prove it. There are warning signals for twinning in the frames and in the data statistics, but not all of them have always to occur. In particular, the L-test is not working well if you've got overlapping reflections, because then the distribution looks like they're all a sum and the crystal is twinned, or in cases of pseudo-translational symmetry. If the data quality is sufficient and the crystal is twinned, the structure can be elucidated. Do not throw away your only crystal just because it is twinned. Measure it and try to solve the structure. But sometimes, in particular with non-merohedral twins, you may save you the trouble if you have another crystal. Here's some literature. Biomolecular crystallography by Bernhard Rupp introduces some fundamental concept. The yeast server, which does the L-test, can be found here. There's a paper, Introduction to Twinning by Simon Parsons, which gives a general overview. If you are interested in twin crystals and anomalous phasing, there's this very good paper by Spicek Dauter. And are we still having the twins around, or did someone sack them? Thank you. Before we do that, any questions at this point? Let's do the questions first. Yes?
It might not be a useful thing to do, but do you know if anyone's done a post-mortem analysis of the interface between domains in the twin, either merohedral or pseudo?
If there has one, I do not know of it. Yes?
Is it still twinning if you've got two species in your crystal but they've got slightly different lattice balances, so they've got slightly different occupancies or something? Would those two species do the same?
It would not. We would, if the species are slightly different and distinctively so, we would not call this a twin. And it would possibly show that you could model it as disorder. So you would do normal twin refinement, and if the difference is really very small, you may be able to model it as a disorder. But it's not a very usual case. And also, crystals that come from two different species are not a twin. So if you have a crystal, if you have your protein crystal and ice is growing on top of it, this is not a twin. This is a crystal with another crystal growing on top of it.
What about if you've got the same crystal but one species has a different occupancy together?
That's not the same species. Yes?
In many cases, the beam is now smaller than the crystal, so the fraction changes during the experiment. Is that included in some of the programs?
To my knowledge, no. So, and this is, of course, a big problem. So the twin fraction actually, so what you can do and what has been done is you take the first 50 frames, integrate them, determine the twin fraction, detwin them, take the next 50 frames. But that is so pedestrian that most users will never be able to do that. And actually, this is something that needs to be addressed.
It's also worth collecting on different parts of the crystal with a small beam and seeing whether you can find a spot that,
Indeed, very often you have a rod, and at the end of it, it's like feathering out and is twinned or split. And the other end of it is good. Yeah.
The other thing is pseudo-translation masks, twinning tests.
Partly. The pseudo-translation, so this has to do with how far the intensities you use for the L-test are away from each other. And you need to make a smart choice in this case. Some programs like Phoenix X-Triage will do so automatically. Another problem for the L-tests are datasets which are very weak. There, again, you may get an indication that it's twinned, but it's not. Ultimately, sometimes you need to actually do refinement for both cases and compare and make the decision based on the map. So because the R value is not giving you a good indication, But looking at the detail in the maps sometimes can be helpful to decide if and how the crystal was twinned. However, these cases are not so common. Yeah?
No, I suppose it's more of a point, but I always regard the way you treat pseudo-merohedral twins as being compensating for the limitations in the instrumentation. In other words, you say that you often see the spot split at high resolution, and that's because it can resolve the slight difference in the cell dimensions between the two at high resolution. If you had a nice parallel beam, decent hues detectors and so on, they'd be split at low resolution as well. And so, obviously you've got
yes,
to treat it
so
with
this
what
is
you've got, but nevertheless there's a limitation of the information of the instrument that actually gives this sort of
yes, that is true, although if you see splits everywhere, so it's true that sometimes you come in particular with a crystal where you think it's not twinned, and you measured it at home source with a CCD detector, and you bring it to the synchrotron where you get much sharper spots, and suddenly you see the crystal is split. So this is common. Yeah. And yeah. So in this case, one of the possibilities for split crystals is sometimes just to make the box bigger and not worry.
Well, yes. Yeah,
it's not the cleanest way to treat it, but it's a possibility.
Yeah, but really all I'm saying is if it's split in the pseudo-merohedral case, and you see that it's like splitting at high resolution, it's also split at low resolution. It's just that you can't see the
yes, that's true. But of course, whether it's split also at low resolution, if the mosaicity would be high, the overlaps would still be very close.
Well, it depends
yes.
on the type of mosaicity.
Yeah. Yeah, that's right. Any other questions? Let's have a quick look. I hope you've all seen this twin. Now, what kind of twin do you think this is? You can just guess. An answer is better than no answer.
Well, if it's twin, is it randomly, or is it sort of non-merohedral?
Yeah, that's right. One domain is merohedral, so both domains are merohedral actually. And what's the twinning like? So how would one domain be translated into the other? Rotation, where? Here? There. If you rotate there, with the axis going through the crystal like this, you would get this tip going to that tip. That's the true symmetry operation of one domain, but it's not the twin law. So yeah, we can see that. If we rotate this one domain by 180 degrees, we end up here. And if we rotate this domain by 180 degrees, we end up here. But what's the twin law? Yes, exactly. So like this. So a rotation by here, which is, of course, the same as a rotation by this, because this is twinning from monoclinic to orthorhombic, which you cannot with certainty say from the look of a crystal, but I want to remind you that crystallography existed long before we had X-rays. And they mainly looked at planes and normals on planes, and the normals on the planes are, of course, the axis of reciprocal space. So this is a pseudo-merohedral twin. I don't know, this might be too small, but you can see that in this one, the two domains are at a 90-degree angle, so possibly a fourfold rotation in this, from here to there, is the twin law. And if you had a look at the period crystal here, if you looked very closely, you will have seen that the two cubes are arbitrarily oriented towards each other. So this is a non-merohedral twin. Well, so much for the examples, and I hope you found this enjoyable, and I see you again in 2 weeks' time.